In this session, we're going to take a look at two different approaches to finding the change in velocity of an object given an acceleration versus time graph. And in this first case, we're going to take a look at a change in velocity of an object traveling with constant acceleration. Now to begin, I'm just going to write down my definition of acceleration, which says that acceleration is a change in velocity per change in time. And what I'm going to do is I'm going to algebraically manipulate this equation to find the change in velocity. So I need to begin by multiplying both sides by my delta t, my change in time. And when I do that, I've isolated my delta v term, or my change in velocity term, and I can rewrite my change in velocity as the acceleration of this object over the period of which it's accelerating. Now in this case, I'm given an acceleration of 2 meters per second squared. So let's just summarize our information. 2 meters per second squared. And if the interval of time over which I'm looking at this object's acceleration is 4 seconds, I can now find my change in velocity by inserting my known values. And now in this case, it will work out to be 2 meters per second squared times a time change of 4 seconds. And notice that this unit of seconds squared cancels out with this unit of second. And now I get a change in velocity of 2 times 4, which is 8 meters per second. Now this is an approach that we've already looked at, and it's a relatively straightforward approach. But now what I'd like to do is develop a geometric interpretation of the equation, the change in velocity equals acceleration times the change in time. Now the geometric interpretation of this equation is that the area bound by the time axis underneath the acceleration curve is the change in velocity. So if I look at the area underneath this curve, I can now find the change in velocity. Now in this case, you can interpret the acceleration as the height of a rectangle. And you can interpret the change in time as the length of a rectangle. So in this case, in this one particular case where acceleration is constant, the area underneath the curve is a rectangle. Now, there's a more general idea behind this that we're going to take a look at in this next more difficult example. So let's take a look at an acceleration versus time graph of an object whose acceleration is not constant, but rather is changing. So let's take a look at a relatively simple case in which it's a nice linear change. That is, as the time increases, the acceleration is going to increase over time. So what our last statement said was that if I want to find the change in velocity, all I need to know is the area bound above by the acceleration curve and below by the time axis over the duration or period of which this object's accelerating. So if I know this area, I can find the change in velocity of this object. Now in this case, this is a simple geometric object. This is a triangle. So in order to find the change in velocity, I'm going to look at the area of a triangle. And if you recall from geometry, the area of a triangle equals 1/2 the base of the triangle times the height of the triangle. Now in this case, the height of the triangle is represented by the change in the acceleration. And the base of the triangle is represented by the change in time. So if I know these two terms, the change in the acceleration and the change in time, I can now find my change in velocity. So I can now rewrite this as 1/2 the change in time times the change in the acceleration of this object. All right, and now in this case, let's assume that our change in time, so let's assume that the time change that we're looking at is 4 seconds. And let's assume that this object accelerates from 0 meters per second all the way up to, say, 2 meters per second squared. All right. So now in this case, you can write the change in velocity as 1/2 of 4 seconds. So we're looking at a 4-second interval of time times a change in acceleration of 2 meters per second squared minus 0 meters per second squared. That's the change in the acceleration. So in this case, we can now rewrite this as 1/2 of 4 seconds times 2 meters per second squared. And now when we do this, notice that this unit of seconds cancels out with this unit of seconds squared, and you're left with 1/2 of 4 times 2 meters per second, which equals 1/2 of 4 is 2, times 2 is 4 meters per second. Now notice, this is a much more powerful approach to use than to use a kinematic equation. So if you recall, when we derived this equation, v final equals v initial plus acceleration times time, we assumed that the acceleration was constant. And in this case, when we have a changing acceleration, this equation no longer holds true. And as a demonstration of that, let's assume that we use this equation to find our final velocity. So if we assume v final equals v initial plus at, and we're looking for the change in velocity, so what I can do is I can subtract my v initial from both sides to find my change in my velocity. So v final minus v initial is now my change in my velocity, which I represent as delta v, and that's going to equal at. Now if I try to use this equation to find my change in velocity given a changing acceleration, what I would find is that maybe I'd use 2 meters per second squared as my acceleration and a time change of 4 seconds. And notice this works out to be 8 meters per second, which is not correct. So this is why it's very important to know where the equations that you use come from, because you can make the mistake of using an equation in a case where it's not appropriate to use.